I want to start today with a number that is so big, it frankly keeps me up at night. 400 billion. That is the low-end estimate of how many stars are in our galaxy. Alone. 400 billion chances for a sun, for a solar system, for a home.
It's a staggering number.
Yeah.
It really is. It's the kind of scale that just breaks the human imagination. You try to visualize it, and your brain just taps out.
Exactly. And for decades, we've been staring at that number, asking that famous Fermi paradox question, where is everybody? Here's where it gets interesting and honestly a little frustrating. We aren't just guessing anymore.
No, not at all. We actually have hard data now.
We have confirmed over 6,000 exoplanets.
That's right. And thanks to missions like Kepler and TESS, that catalog is growing every single day. We aren't just theorizing about planets anymore, we are counting them.
6,000 worlds. And yet the great silence remains. We haven't found a single neighbor. No radio signals, no megastructures, not even a definitive microbe. So the mission for this deep dive is to ask a slightly different question. I don't want to ask, are we alone? I want to ask, are there habitable worlds out there that we are literally staring at but just cannot see?
It's the ultimate question of detection bias, isn't it? Are we alone or are we just blind? And we've got a stack of research here, data from the Planetary Habitability Laboratory, studies on what are called cryptic biospheres,
Ooh, I like that term.
and some fascinating new papers on why advanced civilizations might actually go invisible because of AI.
Okay, let's unpack this. Because the more I read through these sources, the more I felt like we're looking for a needle in a haystack, but we're using a magnet that only picks up, I don't know, glowing hot needles.
That is actually a perfect analogy. In the field, it's often called the streetlight effect. A drunk man is looking for his keys under a streetlight. A cop asks, "Is this where you lost them?" And the man says, "No, I lost them in the park, but this is where the light is."
Right. And in exoplanet hunting, the light is our current technology.
Precisely. Let's just look at the data on those 6,000 confirmed planets. The main way we find them is the transit method.
Okay.
We stare at a star and we wait for its light to dip just a little when a planet passes in front of it. It's basically a shadow puppet show.
Which sounds foolproof. I mean, if something blocks the light, it's there.
It works great,
Huh.
but it has a massive inherent bias. Just think about the physics of it. To confirm a planet is real, you need to see it pass in front of the star multiple times.
To establish a pattern, yeah.
Exactly. So if a planet takes, say, 100 years to orbit its star, you might wait your entire lifetime to see it transit once. You'd never get the data to confirm it. But if it orbits in 3 days,
You see it constantly. You're swimming in data.
you see it constantly. So we're finding the speed demons.
The speed demons and the heavyweights, I'm guessing. Big planets block more light.
Exactly. Big planets block more light and close planets orbit faster. So our map of the galaxy is just, well, it's heavily skewed toward these massive planets that are practically hugging their stars.
This has to explain a statistic in the research that just blew my mind. In a recent analysis of these planets, there was a category called too hot. Do you remember the percentage there?
Oh, I do. It's a humbling number. It was 77.75%.
Nearly 78% of the worlds we have found are scorching hot hellscapes, and only about 4.5% were in the habitable zone.
So if you just glanced at our map of the galaxy right now without knowing how the tools work, you'd assume the Milky Way is basically a collection of hot Jupiters and lava worlds.
But that's just an illusion.
It's likely just an illusion caused by our instruments, like dragging a net through the ocean. But the net has these massive holes in it. You catch a couple of whales and sharks, then you conclude, well, I guess there are no sardines in the ocean.
We're finding the hot Jupiters because they're easy to see, not because they're the most common. It's like assuming most animals in the ocean are bioluminescent deep-sea fish, just because they're the easiest to spot in the dark.
We have a sampling bias that effectively blinds us to the quiet, cool, Earth-like worlds that might be sitting right over there in the park, just outside the range of our streetlight.
Okay, so we have a skewed map. That's problem number one, but let's play devil's advocate for a second. Let's say we do find a rocky planet in that little 4.5% sliver. We find a world in the Goldilocks zone. Not too hot, not too cold. We usually pop the champagne and assume that means Earth 2.0, right?
And that is the trap. We tend to define habitable as exactly like Earth. But the research suggests we need to broaden that definition a lot. There's a classification system proposed by Lammer and his colleagues that breaks habitability down into 4 distinct classes.
And only one of them is what we'd call Earth-like.
Only one.
Okay, walk us through these, because this really changed how I picture aliens.
So class 1 is what you expect. An Earth-like planet, surface water, photosynthesis is possible. This is the standard habitable zone target that everyone gets excited about in the news.
The Holy Grail.
Right. But then you have Class 2. These are worlds that maybe started out Earth-like but evolved differently. Think of Venus or Mars.
Okay, failed Earths.
Or just different Earths. They're in or near the zone, but they went rogue. Venus got a runaway greenhouse effect. Mars lost its atmosphere. But here's where it gets really interesting. Class 3.
What's Class 3?
These are worlds with subsurface water oceans. They don't need to be in the Goldilocks zone. They can be way out in the cold, dark void.
We're talking about Europa here, right?
Yeah.
Jupiter's moon?
Europa, Enceladus, maybe even Ganymede. These worlds have liquid oceans hidden beneath kilometers of solid ice. If you look at them from space, they just look like frozen, dead billiard balls.
So are telescopes searching for things in the atmosphere like oxygen or methane?
They would see absolutely nothing because that ice shell blocks everything. It seals the ocean off from space.
But underneath that ice?
Underneath, they could be teeming with life. Chemosynthetic life, huddled around thermal vents, totally disconnected from the sun.
That's terrifying and exciting at the same time. A whole category of life that is completely invisible to a telescope. You can have a galaxy full of life, but it's all locked in a basement with the lights off.
And then there's Class 4. This is the really weird stuff. Worlds where liquid water isn't the solvent for life.
Like Titan, with the methane lakes.
Exactly. Saturn's moon Titan has lakes, rain, and rivers, but they're made of liquid methane and ethane. It's minus 179 degrees Celsius. Water is as hard as rock there.
But there's still chemistry happening.
Complex organic chemistry, yes. If life exists there, it wouldn't look anything like us. It wouldn't use water. Again, our standard definition of the habitable zone, which is really just the liquid water zone, would completely miss it.
So the life-supporting zone, the LSZ, is actually much, much bigger than the standard habitable zone we always talk about.
Oh, vastly bigger. We are obsessed with finding reflections of ourselves. We look for surface water and oxygen. But the universe might be full of life huddling under ice sheets or swimming in methane lakes. We might be searching for a specific type of loud, wet biology, while most of the universe is running on a completely different operating system.
Okay. Let's say we get lucky. We find a Class I planet. It's rocky, it's wet, it's warm, it looks perfect. Can we assume that if life is there, we'll see it?
You would hope so.
Mm-hmm.
But this leads us to the concept of the cryptic biosphere.
I love that term. It sounds like a sci-fi thriller, the cryptic biosphere.
It implies a biosphere that is effectively hiding. The source material gives a fantastic example from right here on Earth, the Houghton impact structure in the Canadian high Arctic.
This is that crater that looks like Mars, right? I think NASA uses it for training.
Correct. It's a polar desert, dry, freezing. It's just bombarded by UV radiation. If you look at the surface, it is barren. It looks dead. But if you crack open those rocks, specifically the shock metamorphosed, nice just millimeters beneath the surface, there is a green band of life.
Wait, inside the rock?
Yes. Organisms living inside the rock pores to protect themselves from the UV and the cold. They are thriving, but they're completely disconnected from the atmosphere in terms of a massive signal. This is a cryptic biosphere.
So you could have a planet that is technically inhabited, but from light years away, it registers as a false negative.
And this isn't just some niche Arctic thing. One of the papers points out that for a huge chunk of Earth's history, the so-called boring billion years.
The boring billion.
Yeah, before the second big rise of oxygen, Earth itself might have been a false negative.
Wait, really? We had life, but we didn't look like we had life.
Life was mostly microbial. It hadn't yet pumped enough oxygen or methane into the atmosphere to create that disequilibrium we look for. We weren't altering the chemistry of our atmosphere enough to be noticed from space. An alien astronomer looking at Earth 2 billion years ago might have just shrugged and moved on to the next star.
That is humbling. We might be scanning planets that are currently in their boring billion phase. They're alive, but they aren't loud about it yet.
It's something called thermodynamic uncertainty. We assume biology will mess up the atmosphere enough for us to notice, but efficient or cryptic or just early stage life might not. Uninhabited habitable worlds are possible, but inhabited undetectable worlds are also a terrifying possibility.
Okay, so microbes are quiet. I can accept that. They hide in rocks, they live under ice. But let's escalate this. Surely if a civilization advances to the point of building cities and spaceships, they become loud. We've been blasting radio waves into space for 100 years. If there's an advanced civilization out there, we should hear them.
This is where we hit what I'd call the technology trap. And Honestly, this part of the research gave me the chills.
Why?
Because we assume that advanced means louder. But a new paper revisiting Carl Sagan's communication horizon suggests the exact opposite.
Go on.
Think about our own history. We started with analog radio. It was messy, inefficient, and it just blasted signals everywhere. We were loud, we were leaking I Love Lucy into the cosmos.
Right.
But look at us now. We're moving to fiber optics, directed lasers, highly compressed digital signal.
We're getting quieter.
Rapidly.
Yeah.
The paper suggests that the window where a civilization uses detectable leaky radio technology might be incredibly short, maybe just a century or two.
A blink of an eye in cosmic time.
Exactly. As soon as they invent artificial intelligence or, quantum communication, they might go silent. Not because they're dead, but because they are efficient.
It's like the dead internet theory applied to the entire universe.
In a way, yes. Imagine a civilization run by an advanced AI. It wouldn't communicate by shouting radio waves into the void. It would likely use neutrinos or tight beam lasers or something we can't even detect yet. They would be talking to each other constantly, processing unimaginable amounts of data. But to us,
Silence?
silence. The great silence might just be great efficiency. We are looking for the cosmic equivalent of smoke signals, but everyone else is using fiber optics.
Or what about that dark forest theory? Maybe they're quiet on purpose.
That's another possibility. If you think the universe is full of predators, you don't broadcast your location. But even without the paranoia, simple technological progression makes you invisible to our 20th century radio telescopes.
So we're looking for 1950s radio towers, and they're using quantum telepathy or something. This feels like we're running out of options. We can't see the planets because of orbit bias. We can't see the microbes because they're in rocks. We can't hear the aliens because they're on fiber optics. How do we catch them? Is there anything left?
Well, there is one thing that's very hard to hide: energy consumption. Thermodynamics. If a civilization is large, it needs power.
Techno-signatures.
Right. And we're not just talking about Dyson spheres, those giant shells around a star. Those are the extreme examples. One study looked at something much more relatable: solar panels.
Just standard solar panels,
But-
like on my roof.
Silicon-based photovoltaic cells, yeah. They reflect light differently than rock or water or vegetation. Silicon absorbs visible light and reflects infrared in a very specific way. It creates a spectral edge.
So if a planet is covered in solar farms, it would glint differently to a telescope.
It would have a spectral fingerprint. But here's the catch, and connects right back to our detection limits. To be seen by a next-gen telescope, like the proposed Habitable Worlds Observatory, the study found a civilization would need to cover about 23% of their planet's land area with solar panels.
23%. That sounds like a lot.
It is massive. Think about Earth. We have cities, farms, forests. Covering a quarter of all land with solar panels is an immense industrial undertaking.
How does that compare to what we might need?
Well, the study did a comparison. If you took 30 billion humans, that's 4 times our current population, and gave them all a high standard of living, we would only need to cover about 8.9% of the land.
So even with 30 billion people, we would still be invisible.
Unless we were terribly inefficient energy hogs, yes. We would be below the detection threshold. We are looking for civilizations that is expanded to an industrial scale that just dwarfs ours.
Okay, what about pollution? I saw a mention of looking for our own mistakes, but in other atmospheres.
Yes, industrial pollutants like nitrogen dioxide, NO2, or CFCs, chlorofluorocarbons.
The stuff that killed the ozone layer.
The very same. CFCs are a strong technosignature because nature doesn't really produce them in any quantity. If we see a planet with oxygen, water, and a heavy dose of CFCs, that's a pretty smoking gun for an industrial civilization.
It's funny that our best hope of finding friends might be detecting their smog.
It's a bit ironic, isn't it? But it highlights the central theme here. Detection requires an anomaly. We need to find things that nature shouldn't be doing on its own.
Which brings us to the final concept I want to touch on. We've talked about biosignatures, life signs, and technosignatures, tech signs. But the sources mention something called a peri-biosignature. What is that?
This is a really clever way of rethinking the search. Peri means edge. The idea is to look for life at the edges of the habitable zone.
Explain that.
Okay, imagine a planet that is right on the outer edge of its habitable zone. By all the laws of physics, it should be frozen solid, a snowball.
Right.
But when we look at it, we see it's actually liquid. It's warm. That's the anomaly. That's the signature. Maybe life on that planet has evolved to pump out greenhouse gases, CO2 or methane, specifically to keep the planet warm. Biology working overtime to terraform its own home.
So the planet itself is the signal. The fact that it's not frozen is the proof of life.
Exactly. Life is a stabilizing force. If we find a world that defies its local thermodynamics, a world that is too warm, or too chemically balanced, or too stable, that anomaly is the signature. We shouldn't just look for Earth-like. We should look for the weird.
It's like walking into an empty house in the middle of winter and finding one room is perfectly warm. You know someone is in there keeping the fire going.
That is the perfect metaphor. The universe is cold and indifferent. If we find a warm room, something is paying the heating bill.
So to wrap all this up, we started with the great silence. But it seems like the silence might not be because the universe is empty. It's because the universe is shy or hidden or just way more efficient than we are.
We have to remember that our search has only just begun. We're like a person who dipped a single cup into the ocean, came up with no fish, and concluded there are no fish in the entire ocean.
And we're realizing we might need a bigger cup. Or maybe we need to stop looking for the fish and start looking for the water they displace.
Or the bioluminescence deep, deep down in the dark.
Exactly. It changes the way you look at the night sky. It's not necessarily a graveyard. It might be a library where everyone is just reading quietly.
And we're the ones shouting in the hallway.
I love that. So here's the thought I want to leave you with today. We focus so much on finding a twin Earth. But what if the first life we find isn't on a blue marble? What if it's a heat signature on a frozen rock, or a glint of silicon on a jungle world, or just a planet that refuses to freeze?
We need to look for the anomalies, not just the reflections of ourselves.
Are we alone, or are we just using the wrong senses? Something to think about next time you look up. Thanks for diving in with us.
Always a pleasure.